So our next speaker is Diptesh Kumar Saha from NISER Bhubaneswar. He is going to talk about von Neumann algebra associated to Young-Baxter operators. Yeah, over to Diptesh.
Okay, thank you, sir. So first of all, I want to thank the organizer for giving me this opportunity to speak. And as sir mentioned, the title of this talk is von Neumann algebras associated to the Young-Baxter operators. And this is a joint work with Pachu Gopal Bikram, Rahul Kumar, Rajiv Mohanta, and Kunal Mukherjee. Okay, let's get on to the talk. Okay. So the outline of my talk is like, so we are going to talk about a von Neumann algebra. So for that, first we need to define a Hilbert space on which the von Neumann algebra acts. And then we define the Young-Baxter von Neumann algebra, and we see some structural properties of some sub-algebras and the von Neumann algebra itself. So for example, we see that there are special sub-algebras which are singly generated and which are massa, and Young-Baxter von Neumann algebra is in fact a factor with some more condition on that. So let us begin. So in this talk, the H is always a separable Hilbert space, and the inner products are always linear in the second variable. So von Neumann algebra is nothing but a unital star subalgebra, which is a subalgebra of V of H, which is SOT closed, and equivalently it is WOT closed. And by the famous bicommutant theorem, it is same as the double commutant of itself. And von Neumann algebra is said to be a factor if its center is trivial. Okay, so now let us construct the Hilbert space on which the von Neumann algebra act. So we start with a real Hilbert space, which is denoted by HR, and we complexify it. And then we define so all these construction are due to Bojico and Spitzer in 1994. So they defined a self-adjoint strict contraction H tensor H, which satisfy a certain braid relation. So since you can see that T is a operator defined on H tensor H, so 1 tensor H and T tensor 1 are nothing but the amplification of the proper amplification on the space H tensor H. And such an operator is known as the Young-Baxter operator. Now, given a Young-Baxter operator, we are going to define an inner product on the full Fock space. So the next few slides are actually involve some technicalities. So let us skip those. So suppose now we have we all know there is a full Fock space. So full Fock space is nothing but a direct sum of Hilbert spaces, which are tensor products of a Hilbert space, and H naught is defined as a one-dimensional space where omega is nothing but a fixed unit vector. So now we have a Fock space and a full Fock space, and we have a Young-Baxter operator. Now we are so what Bojico and Spitzer did, that they cook up for every n they cook up a bounded operator on H tensor n, such that this Pn becomes the strictly positive and invertible operator. So since this operator is positive, then if one associate, because of this result, if one associate the inner products like that, so xi eta, if we define as, so when xi and eta are coming from the same particle space, then if we define the association like inner product of xi and Pn eta, then that defines a definite inner product on the inner tensor product. And as a result, they defined a inner product on the full Fock space. Now we take the completion of the full Fock space with respect to the norm generated from this inner product, and this twisted Fock space is this Fock space, this completion of this full Fock space is known as the T-deformed Fock space. So now let us let us go to the definition of the von Neumann algebra, of the Young-Webster von Neumann algebra. So it is defined. It is generated by some self-adjoint operators. Now, the full Fock space already have operators like creations and annihilations. The creation operator is defined on the full Fock space. It acts on the vacuum vector omega as L psi of omega is psi, and L psi on the simple tensor of n vectors. It just adds psi to the left. So this is the left creation, and this is the annihilation operator on the full Fock space. What does it do? It just annihilates the vacuum vector omega, and when it acts on the simple tensor psi on psi n, it just annihilates the first component of the simple tensor. Now these operators, this is creation on the full Fock space, and this is annihilation on the full Fock space. But these operators we are not going to work on. So we take the creation operator as it is on the full Fock space, which is defined on the FTH, but we twist the annihilation a bit. So this is we twist the these are called left creation and left annihilation operators. So this is, we just multiply the d star psi with the quantity. So what are TIs? TIs are the proper amplifications of T itself again. So this acts on H tensor n. So now we have a creation and annihilation operator on the T Fock space. Now what we are going to do, we are going to define. So now note that these operators are actually densely defined. So for defining the von Neumann algebra, we need bounded operators. So Bojeco and Speicher, thanks to Bojeco and Speicher in 1994, they actually proved that the creation and annihilation operators defined on the full Fock space are actually bounded, and they are adjoint to each other. So the bound is given by, for every psi, the bound is given by norm psi by root over of 1 minus lambda. The lambda is nothing but the norm of T. Now consider the self-adjoint operators S of psi, which are nothing but the sum of the creation and annihilations, and we generate the von Neumann algebra MT, and we vary the psi over the real Hilbert space. So, and this is actually the Young-Webster von Neumann algebra, and we define a state on this von Neumann algebra as omega inner product of omega x omega. So it is clearly this is a state. If you put 1, this is nothing but the norm of omega, which is nothing but 1, which we already have assumed. So now we have the von Neumann algebra in our hand. So and the state on it. So the one question asked that whether this state is a trace or not. So what Bojeco and Speicher did, that the vacuum state, the defined above, is a trace if and only if it satisfies that the Young-Webster operator T satisfies such a inner product condition. So this inner product condition looks like a bit weird, but what you can see that suppose these xi's are so if we fix a orthonormal basis of the real Hilbert space, so this condition is giving us so if I can show the next slide. So suppose this is the orthonormal basis, then this T, I, J, R, S are nothing but the inner products defined in the previous slide. So what it says that the coefficient of the T satisfies a really nice condition. And what they showed, that it is a trace if and only this condition is satisfied. And as a result, they showed that if this omega is a cyclic and separating vector on MT, and as a result that phi is a faithful. So what we get that the MT, FTH, and the omega is actually a GNS triple. And yeah, so GNS triple for the state phi. Okay. So this suppose this T has a, so for a fixed orthonormal basis, T has a matrix representation like that, then our creation and annihilation operator satisfies a bunch of commutation relations. So these commutation relations are actually generalization of some very nice commutation relations. So one thing I want to mention in this slide is that in this slide also, that T satisfies a weak product condition if actually, so this set is finite. This set is nothing but, so suppose for every, if you fix I and j, then if you see that this linear sum, this is infinite sum. So what it says that T satisfies a weak product condition when this linear sum becomes actually finite. So I think this is wrongly written. So this is not equals to 0. That is not equals to 0 is finite. This in our product not equals to 0 is finite. So yeah, sorry. Okay. So why this Von-Neumann algebra is interesting? Actually, this T Young-Baxter Von-Neumann algebra subsume the cases for the free Gaussian functor due to Voiculescu, and also the Q Gaussian Von-Neumann algebras by Bhubaneswar and Speicher. And these two Von-Neumann algebras are actually very well studied in the literature, and both of them are actually the factor when dimension of feature is actually greater than or equals to 2. Then suppose now we get some results. Suppose for a xi nature, we define the singly. So what is a singly generated Von Neumann? It is a Von Neumann generated by single element. The Sji is as defined before. Okay. So what we got that whenever this dimension of HR is finite, and if we impose the condition on this T, the special condition, if we find a vector, find a eigenvector of this T of this special form corresponding to the eigenvalue Q for norm Q mod Q is less than or equals to the norm of T, then we show that M xi naught is actually a strongly mixing massa. As a result, it is a singular massa. So what does it mean by a massa? Massa is a maximal abelian self-adjoint subalgebra of T. That means you cannot find a proper subalgebra of MT which contains M xi naught. So this result says that when dimension of HR is finite, then we get the result. But what about dimension of HR is infinite? For that, when dimension of H is actually infinite. So remember that we always assume that the Hilbert space is separable here in this talk. So when this is Aleph naught, then we get a similar result again, but then we have to assume a bit more condition, that the eigenvectors E mu naught should come from an fixed orthogonal basis of HR, for which the weak products condition should be satisfied. So for infinite dimension, if we assume these two conditions, we are getting the same result. And using these two conditions, using these two results, we get the factoriality of the Young-Baxter Von Neumann algebra. So this is the main result, that when a dimension of HR is actually finite, then we get that the Von Neumann algebra is a factor, and also for the dimension of HR is when Aleph naught, then also, and the weak product condition is satisfied, then MT becomes also. Also, this condition, one thing I want to remark here, that this condition is actually very much helpful for us, because for this condition, the subalgebra, that the singly generated subalgebra M xi naught, for that the GN space becomes really nice. So this condition was very much helpful for us. So okay, thank you. Okay, thank you. This is my talk, and for the reference, the most of the constructions one can find in the paper Bhubaneswar and Speicher, and for the type 3 invariant of the Von Neumann algebras can be found in the paper by Bikram and Mukherjee, and this is a paper which is.
Yeah, thank you. If anyone has any question, we have 2 minutes.
So what was the comment regarding this free groove thing, this phenomenon?
So whenever the T is 0, then the creation and operator satisfies this condition, right? If you find that
right,
T is 0, this is L star E1, L star E is equals to delta ij1. So if you define the Von Neumann algebra operators defined by this is the free groove factors.
This is always a factor then when T is.
Yeah.
And you prove that when you deform it, then it's also a factor when it has some condition.
Yeah, right.
Okay. All right. Thanks.
Yeah. Any other question? Okay. So thank you for the nice lecture.